Okay, I'm going to do a short video here just to cover Lineweaver-Burke plots, and then we'll switch to another section, another video, another batch of notes for the next part of the class. This is the last lecture before exam 3. Well, this one and the next one, so I'll try to keep it short since this is new material that isn't on the exam, and I understand that people want to focus on the exam. So we talked last time about the Michaelis-Menten mechanism and the Michaelis-Menten rate law, and where is it up here? Boy, where is it? There it is. So the rate of reaction, enzymatically catalyzed reaction, is equal to Vmax times 1 over 1 plus quantity Km over S. And remember that Vmax is equal to K2 or Kcat, if you like, times the total enzyme concentration. And remember, this total enzyme concentration isn't just the free enzyme, it's also the sum of free enzyme plus bound enzyme, so it's a constant. And Km is equal to K minus 1 plus K2, or we'll call it Kcat from now on, divided by K1. If K minus 1 is 0, no, let's say, yeah, if Kcat is 0, in other words, if the rate of reaction is slow, then this would just be a Kd for the binding of the substrate to the enzyme. And Km is often used that way. As it stands right now, it has units of molar concentration, which means that this ratio, Km over substrate concentration, is unitless. And also, this quantity Km over substrate concentration, remember, is the quantity that matters in a plot of enzymatic production velocity versus substrate concentration. It's the thing that scales the x-axis, and Vmax is the thing that scales the y-axis. All right, that's a little bit of reminder. I think probably most people don't need it, but, well, what the heck. Now we're going to talk about Lineweaver-Burke plots. Let's suppose you do a measurement. You collect some data on the velocity of enzyme-catalyzed production of product versus the substrate concentration. So you measure initial rates of reaction in the presence of an enzyme and then stop the reaction so it never goes to the point where you start depleting the substrate concentration. And you do that for several different initial substrate concentrations, and then you plot that like we did up above here, the velocity that you measure versus the substrate concentration in units of Km here, basically. And you get a curve that looks like this. Can you tell if that's Michaelis-Menten or not? And the answer is not really by eye. So what's a good test for whether something obeys Michaelis-Menten or not? And a good test, as in many other examples throughout this semester, is to find some relationship that would give you a straight line if the enzyme obeys Michaelis-Menten kinetics. And we can get that easily. We just take 1 over this side and 1 over that side. And if you rearrange a little bit, that gives you this relationship. 1 over the velocity is equal to Km divided by Vmax times 1 over the substrate concentration plus 1 over Vmax. And that's in the form y equals mx plus b, where m is the slope, and that's equal to Km over Vmax. And the offset b is equal to 1 over Vmax. And what that says is that a plot of 1 over velocity versus 1 over substrate concentration should give a straight line, like in this picture. And furthermore, the slope of that straight line will be equal to Km over Vmax, and the intercept of that straight line on the y-axis would be equal to 1 over Vmax, which means that Km will be equal to the intercept, 1 over the intercept times the slope. Or in other words, Vmax times Km over Vmax, which is obviously just equal to Km. All right, so let's do an example of that. I think many people are already familiar with Lineweaver-Burke plots. They're very common in the biological sciences. And so let's do an example. Let's suppose we have this chemical reaction and it is catalyzed by this enzyme carbonic anhydrase, which is oftentimes written over the arrow symbols between them two. This is the reaction that's catalyzed, and this is the enzyme, which of course doesn't appear as either a product or a reactant. And here's the data we collect. We collect something for CO2, dissolved CO2 concentration, right? Not a pressure of CO2, but a millimolar concentration of dissolved CO2. We also collect velocity, and notice the units in millimolar per second. It's convenient to have the same concentration units in both columns here, but it doesn't have to be. In real life, you're likely to encounter situations where the units aren't quite so nice between these two, but in this case I've made them compatible. Now, because I want to make a Lineweaver-Burke plot, I make two more columns, one with 1 over the carbon dioxide concentration, and one with 1 over the velocity. And so instead of 1.25 and so on, I get 0.8 going down to 0.05. And likewise, instead of 2.78 going up to almost 17, I start with 36 and end up at 6. And so I make a plot that looks like this, roughly, just drawn by hand. Along one axis are the numbers from this column. Along the other axis are the numbers from this column. I plot the two relative to each other. And in this case, since this is made up data, of course I do get a straight line. But it is possible, it happens in actual life, that you've got an enzyme that doesn't obey Michaelis-Menten kinetics, and in that case you may not get a straight line. There are other mechanisms that I think probably will give you a straight line with a Lineweaver-Burke plot. I'm actually not sure about that, but I wouldn't be surprised. So it isn't definite proof. Getting a straight line isn't definite proof that you do have Michaelis-Menten kinetics, but it is proof that it might be Michaelis-Menten kinetics. And if you get a curved line, then you know for sure you don't have Michaelis-Menten kinetics. All right, that being the case, we got our straight line. We want to get the Michaelis-Menten parameters right. Km is one of them, Vmax is the other one. The intercept here gives us 1. That's 4.0 seconds per millimolar, right? It's got units of 1 over velocity. Velocity is millimolar per second, so the units of the intercept are seconds per millimolar. And that means the velocity, Vmax, is equal to 0.25 millimolar per second. Note the units because we do have to keep the units compatible, and it's very common to use all kinds of different units in this setting, so you've got to be aware of them and careful with them. The slope then is equal to the change in stuff along V, along the y-axis. It's delta y over delta x, right? Versus the change over stuff along the x-axis, so delta 1 over s. And that's these numbers, and that gives us 40. Again, notice the units. This is seconds per millimolar up here. This is 1 over millimolar here, so you get units of seconds for the slope. And that means, yes, here's the Vmax again, and then Km is slope times Vmax, or else slope over intercept. And that's equal to 10 millimolar, which means that for this particular reaction, you get half maximal velocity at a concentration of 10 millimolar, which is somewhere in here and in these data. And below that, you're going to have less than maximal velocity. Your enzyme's a little starved for substrate. And above that, you're going to get greater than maximal velocity. You're starting to saturate your enzyme, in fact. And then we can calculate Kcat if we know how much enzyme we put in. And it did say that somewhere. Yes, here it is, 2.3 nanomolar. So taking the Vmax in millimolar per second and changing this nanomolar units to millimolar, you know what? That's wrong. That should be 10 to the minus 6 there. millimolar because it was nanomolar, which means this should be 1.1 times 10 to the minus to the plus. I think it is 5. I think that was right. I had the wrong number there. Right, I think it was. It's still very fast. I think that's right. Let's check that just to make sure. I don't need to. I'm pretty sure that's right. All right, so I got the right number even though I put the wrong units there, or the wrong number there, exponent there. And so the enzyme will saturate, yes, for concentrations of CO2 much greater than 10 millimolar. And that's it for this batch of notes. We'll switch to another batch of notes for the next lecture.